Hey everyone, welcome to this channel, and today we will talk about reliability, scalability and maintainability in software systems. Let's start. If you are a software engineer, you might have heard about a lot of buzzwords like big data, sharding, eventual consistency, strong consistency, gap theorem, real time, and lot more other words. Large-scale software systems are relatively new in comparison to the other domains like automobile or pharmaceutical industry. But in the last decade, it kind of exploded, and the value provided by software systems are revolutionizing other industries as well. So why are these buzzwords important, and why is software system design important? In the last decade, the amount of data observed by internet companies such as Google, Amazon, Meta, Microsoft forced them to create new tools to enable them to efficiently handle the scale at which they are operating. These tools help these large-scale systems to facilitate the three important things: reliability, scalability, and maintainability. We can call it three pillars of software system design. A lot of these tools are open source so that others can contribute, and these tools will evolve much faster and help the software industry as a whole instead of individual organization. Computation power is rarely a limiting factor in modern software applications. The main problem is the amount of data and the speed at which it's changing. Remember the tools we were talking about? So modern applications are built from standard building blocks which provide commonly needed functionality. For example, databases to store the data, caches to speed up reads, stream processing, send a message to another process, RPC, HTTP to communicate between services, batch processing, periodic processing of large amount of data. Above are some really common functionalities you might have observed if you are an experienced software engineer. Most of the above functionalities can be implemented using already available open source or proprietary tools. Most engineers would not even think about writing a new database from scratch. And if you can write a really great database from scratch, well, congrats, you'll be rich. There are so many tools available in the market that even an expert engineer might get confused which tool to use. So fundamental knowledge of these tools are important to build reliable, scalable, and maintainable applications. Now, since we have set up the stage, let's dive deeper into three concepts. We all have a general understanding of what it means for something to be reliable or unreliable. When it comes to software systems, people typically expect the application to do what the user wants, the application to handle user errors or unexpected use, good performance for the intended purpose, and protection from unauthorized access and misuse. Reliability means the system continues to work correctly even when unexpected events occur. These unexpected events are called faults. Systems that can handle these faults are called fault tolerant. However, the term fault tolerant is somewhat misleading. It is not possible to tolerate all types of fault. For example, if an asteroid hit the Earth and all servers went down, tolerating this type of fault would require web hosting in space. Well, good luck getting that budget item approved. That means we can only tolerate certain types of faults. These are hardware faults, software faults, and human errors. Let's talk about hardware faults. Hard drives are estimated to have an average lifespan of 10 to 50 years. In a storage cluster with 10,000 disks, we can expect one disk to fail per day on average. To decrease the fault rate, we add extra copies of the hardware components. This is known as redundancy factor. If one component fails, the other redundant component can take over. Even the entire data centers are duplicated as a backup plan in case of a natural disaster destroys the original center. Software errors. Hardware faults are relatively easy to anticipate. Systematic errors within the systems are harder to anticipate. It could be some software bug produced by an intern, some process used up shared resource, CPU time, memory, disk, or network bandwidth. There is no quick solution of the problem to the problem of systematic faults in the software system. Things which can help is carefully designing the system and thinking about the interaction within the system, thorough testing, process isolation, allowing process to crash and restart, measuring, monitoring, and analyzing system behavior in production. Human errors. Humans design and build software systems, but humans are known to be unreliable. So how to make system reliable in spite of unreliable humans? Well-defined APIs. Design the system in a way that minimizes the opportunity for error. Decoupling the places where people make the most mistakes from places where they can cause failure, like providing a non-production sandbox environment where people can explore and experiment safely. Testing thoroughly, from unit test to whole system integration test and manual tests. Set up detailed and clear monitoring such as performance metrics and error rates. Monitoring can show us early warning signals and allow us to check whether any assumptions or constraints are being violated. Scalability. Even if the system is working reliably today, it doesn't mean it will work reliably in future. One of the most common reasons could be increased load. Perhaps the system has grown from 10,000 concurrent users to 100,000 concurrent users. Scalability is used to describe if the system is working as expected with increased load. When your application is being used by a large number of users, the load can increase. Increased load can be described with the numbers, which we call load parameters. It can be requests per second, the ratio of reads to writes in a database, the number of simultaneously active users in a chat room, hit rate on a cache, or something else. So how do we maintain good performance when our load parameters increase by some amount? There are two solutions here. Scaling up, which is also called vertical scaling, moving to a more powerful machine, or scaling out, which is called horizontal scaling, distributing the load across multiple smaller machines. Distributing load across multiple machines is also known as shared nothing architecture. A system on a single machine is often simpler, but systems at large scale can't avoid scaling out, which is much more complex. Some systems are elastic, meaning they can automatically add computing resources when they detect a load increase, whereas some systems are scaled manually after analyzing their capacity. An elastic system is useful if the load is highly unpredictable, but manually scaled systems are simpler. Let's talk about maintainability. The cost of software is not in its initial development, but in its ongoing maintenance. An important part of this is fixing bugs. Other important things could be keeping the system operational, handling failure, adapting to new platforms and tools, new use cases, repaying technical debt, and adding new features. The easier it is to maintain the software, the lesser the cost of development will be. We should design software in such a way that it will hopefully minimize the pain during maintenance. We should focus on operability, make it easy for operations teams to keep the system running smoothly. Simplicity, make it easy for new beginners to understand the system, but removing the complexity. Evolvability, make it easy for engineers to make changes to the system. So these were the three pillars of software system design. Keeping a system reliable, maintainable, and scalable keeps the development cost low and user adoption high. There is no easy fix to make a system reliable, scalable, and maintainable, but there are certain patterns and techniques which keeps reappearing in different kinds of application. I will talk about these patterns, techniques, and tools in further videos. Thank you.